Hello and welcome back. Our topic for this video is going to be isotopes. All right. I have two atoms drawn up here on the board already. All right. The first one should look somewhat familiar to you. This is what I drew in the previous video for carbon. Okay. And I've labeled this one carbon 12. Okay. That 12 coming from the atomic mass with our 6 protons and our 6 neutrons. Over here I have carbon 14. Okay, carbon 14 is an isotope of carbon 12. Okay, carbon naturally wants to exist as carbon 12. Okay. You've got a balanced number of protons and neutrons in the nucleus, and that allows that to be a stable nucleus. With carbon 14, what we have is we have the addition of 2 additional neutrons. Those 2 additional neutrons here, and we'll color these in because these are going to be essentially what makes carbon 14 a little unstable, because we're not balanced inside the nucleus anymore. And in terms of that, what'll happen with any element that is an isotope of a naturally occurring element, it's going to want to get rid of that extra. So it's going to want to shoot those neutrons out to go back to its normal form. So in terms of isotopes, okay, those extra neutrons are what make the isotopes unstable. And those unstable isotopes very often are going to be radioactive, all right? Because of the instability within the nucleus there, all right, and wanting to get rid of those extra neutrons. So typically isotopes of an element are radioactive, okay, and in terms of those radioactive isotopes, typically if I say the word radioactivity, most people are going to think of something that's not good. It's not beneficial, all right, and part of that is true. Okay, radioactivity, or if we hook this up to something that you might be more familiar with living here in New Mexico, radiation from the sun, okay, that causes damage to DNA, okay? Essentially what it does is it causes changes in the DNA structure, and we'll talk more about those changes a little later in the semester. Those changes are known as mutations, all right? So radiation causes mutations from those unstable neutrons shooting out of the nucleus, all right? And in terms of that, radiation and radioactivity can be damaging to the living cell. All right, because of its potential for damaging DNA. All right, so here in New Mexico, where you can kind of relate to that is if you've ever gone outside, forgot to put on your sunscreen, and you end up with a nasty sunburn. All right, the UV light from the sun also has the ability to damage your DNA. All right, when it damages your DNA, that can cause the mutations in the cell. Those mutations in the cell are what can give rise to skin cancer, all right? It doesn't always. It's not like you get one sunburn and you're doomed, you're going to have skin cancer. It doesn't work that way, okay? Typically, it's repeated exposure. There's also a role of genetics in there. Some people are more susceptible to damage to the skin cells than others, all right? But in terms of that, radiation, typically when I bring that up, you think of something negative, okay? But in terms of your future career as a health profession, all right, radiation can also be used as a tool, okay? And in terms of where you're going to use radiation as a tool are going to be in things like CAT scans or PET scans. Oops, that's not a very good looking C, is it? PET scans, okay? Because essentially what happens with those tests is the patient is injected with a radioactive isotope, all right? You may also hear this referred to as a heavy element. It's heavy because it's got additional neutrons in there, okay? So in terms of our mass with carbon 12 and carbon 14, all right? Our carbon 12, the atomic mass, is still going to equal 12. But our atomic mass associated with carbon 14 is going to be larger. It's going to be 14. So you'll sometimes hear these referred to as heavy elements. And that just gets to the difference in the mass between the two. Okay? But what we're talking about is something that is radioactive. And there are degrees to it. Some elements are more radioactive than others. I'm not concerned with you knowing which ones are more radioactive than others. What I want you to take away is what an isotope is, okay? And how those isotopes can be used in healthcare, all right? So in terms of that, those heavy elements can be used as a tracer. Which means with the imaging and the technology we have, that technology can pick up the difference between the heavy element and the regular element. Because you've got carbon that makes up every single cell in your body, carbon 12. You don't have carbon 14 that makes up every cell of your body. So if you have cells that are going to use that particular isotope, it will be sucked up by those cells that are going to use it first, all right? And those CAT scans or those PET scans can be used to monitor things like tumor growths, all right? Tumors typically need a lot of energy in order to survive. So typically what happens is you get the injection of a radioactively labeled glucose, okay? So in terms of that, with these imagings, you can use natural isotopes in them. You can also use normal molecules that are tagged with one of these isotopes, okay? But the isotope, essentially, it's a tracer. It's allowing the healthcare professional to use the technology to be able to visualize something that's not going right within the body, okay? In the case of tumors, radioactive glucose, that tumor is going to suck up that glucose preferential to other cells within the body, okay? You can also look at metabolism of other diseases as well. It can be used to trace things like Alzheimer's, to image the brain, okay? It can be used to follow oxygen use within the body. But essentially, this is a great tool for healthcare providers to see what's going wrong, potentially, with a patient, okay? And in terms of getting back to that, the isotope is where that tracer comes from, all right? Hopefully that makes sense. If you have any questions, please let me know. Otherwise, thank you for your attention.